Okay, this is an introduction for structured electronic design. Just some course information that I want to give you, some general information that you know what we are doing and who it is doing everything. So what is the intention of this course? What are we trying to do? We are trying to let you master the transistor level design of application specific amplifiers. That is what we are going to do in this course. Um, and the method that we will use is, well, as of now, we will present and explain all kind of material from structured electronic design method. And we will stepwise apply this theory in the design of an active antenna. We also did this in the bachelor course, but in the bachelor course, the implementation technology for the active antenna was an operational amplifier, was just, let's say, a circuit board technology. And now we will use a CMOS 18 implementation of the active antenna. We changed the specification a little bit, but that I will show you later. So basically we do the same thing, but now we are going to do it on transistor level, and especially CMOS 18. The means that we are going to use for this, well, we have a course website. The course website that I am presenting this material from is completely copied to Brightspace. So basically you only have to be on Brightspace. You can see everything on Brightspace. And so we have teaching assistants translating the site to the Brightspace environment. Web lectures will be recorded, as Chris said, and we will try to publish them as soon as possible. So hopefully every time the same week. The book is Structured Electronic Design Edition 1.2. I just had a question if 1.1 was still was okay as well. Well, it is okay. You can find errata on the website of the book, and that is there are not really big changes. Some page numbers have changed, but it's not really a very huge change. So you don't have to buy a new book if you have edition 1.1. If possible, if and useful, we will do some demonstrations as well to elucidate the material. And we have isolated design problems that mostly related to the design of this active antenna. So we are going to design one stage and then another stage and then put it together step by step so that at the end the whole thing is working. And let's say that is every time we do one subject, we try to relate this subject to that part of the design. We have polls and quizzes. Our first poll you have seen, that was, did you have the book, yes or no? We have other polls, and we will give you quizzes on Brightspace as homework. We have one big pool of questions that we are generating, which means that poll questions and quiz questions are coming from the same pool and have the same, let's say, character as the questions that will be at the final exam. So that can be interesting for you, that you have an idea that, okay, if you say this type of questions you get during a poll, and you can also expect this at your final exam. And we will do a test exam as well. So exercises, well, everything will be on Brightspace and you will find it there. We try to do at the end of the course also a kind of mini masterclass, which means that we are going to discuss the design and your contributions to the design that you did from the homework. And it means that you are explaining to each other. I hope that will be possible because the group is quite large, but we will do our best. You will explain to each other and discuss with each other the work that you did. I think this is also making it a little bit more vivid than just having us talking and you listening. So that is about the objective, method, and means. We have some tools. Most of you know already our symbolic circuit analysis tool, SlideCap. But there is a new version. So the version that you know and the version for the book examples is all MATLAB version. But unfortunately, things are happening with MATLAB in a direction that, let's say, that is not really helpful in getting a good tool. Let's say I wrote a complete new version in MATLAB and not in the symbolic toolbox, but it's like 20 times slower than the version in the symbolic toolbox. Although this MATLAB version uses the symbolic toolbox, but the shell that MATLAB is building around it is really slowing things down. And why not migrate to open source software? And that's what we did in the past few months with the teaching assistant. We migrate to Python with the engine that we use as Maxima, version 1.0. You can find it on the website, and it's compatible with Jupyter Notebooks. So if you are familiar with Python and Jupyter Notebooks, maybe this might be an option for you. I will try to do everything in both versions for this course. So you don't have to migrate. You can keep on MATLAB, the MATLAB version if you want to do. But if you're new to this, maybe you better do immediately the Python Maxima version. This is it's not a clickable link, but this is the website to SlideCap. So you can find all the information there about the installation and the manuals, blah, 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 etc. Then, of course, for numeric circuit analysis, well, basically we use LT-SPICE. We have a CMOS 18 library that we also use in the book example and for the antenna design. That is just, it will later become clear how you can download it. And that's, we also have an extra Jupyter Notebook virtual machine. Next year, it will be integrated with this Python version of SlideCap, but now it is just a tool we already developed last year, and it's in a virtual machine, and it facilitates in plotting all kinds of device characteristics. So let's say you want to see a GM of a MOSFET over current, and then you can plot it there, and it's really very helpful during design. You can download it, and later on I will show you the links where it is. I think that is next week, by the way. The staff, well, you already know Chris, I guess. You already know me. Well, by now you know me. I'm talking to you. If you have questions, please contact Marion de Vlieger. You can also email us, of course, but if you want to make appointments, it's better to do it through the university channel. And then your grade. How do you get a grade for this course? Well, we have, what you have to do to get a good grade is attend the lectures, of course, actively participate during the lectures, that helps. So if we have polls, please participate in the polls. Study the material in the book. The book is really good to have because there's lots of more text in the book than there will be on the sheets, of course. Of course, I will try to explain everything in the presentations, but it's good to have background information and reference to literature from the book. So please, you won't make me rich with the book because it's quite low price and there's no earning at all for me. So don't worry about that. It's better to have it. It will help you having a good grade for this course. Make the exercises. It will help you. Some of those will also count for your, can also contribute to your final grade. And of course, it helps if you also make the complete design of the active antenna. But if you really want to become a good designer, go beyond. And that is, if you have design ideas, learn how to verify and falsify yourself. Because later on, if you are working in a company, you cannot ask to colleagues, is it correct what I did? Of course, there will be reviews, but they will trust that you know how to verify and falsify yourself. That's why you did an academic study. So try already to do this, and we can help you with it. In this course, we have provided basically the tools for it. And of course, if things are unclear, don't hesitate to contact us because we will be there for you. There is a lot of prerequisite knowledge. We have, last year, we have had some students, and many students come from abroad and didn't do their bachelor at the University of Delft, but also some students can come from other faculties in Delft and they didn't do, for example, the bachelor electrical engineering. So bachelor electrical engineering is a must-have for this course. Otherwise, you have really problem with understanding network theory and all this concept from it. Of course, we can help you. There is a complete homologation program that you can find it on Brightspace. And that is also for foreign students who didn't do their bachelor in Delft, because this code, EE4109, is structured electronic design in the bachelor's course in Delft. And if you don't have, if you don't didn't attend the bachelor course in Delft, then you don't probably know about the asymptotic gain model. Maybe you don't know how to estimate poles and zeros in networks. The concept of negative feedback is done completely different as in many other courses. So it's all in the book. It's other chapters in the book. You can see in the book where it is, but it's really a must have. I will try to, every time if we use knowledge, so prerequisite knowledge from this EE4109, I'm trying to mention it so that you know where to go. But there's a complete website for homologation program, including videos, presentation, etc. So that should help you, because we decided, let's say 1 or 2 years ago, to not do all this stuff again. Let's say 2 years ago, we still did a lot of this basic knowledge in the master program, but now all of this basic knowledge is assumed to be known, and we don't do it again in the master's program. We are going to use the results of the previous bachelor of the bachelor course. So please be aware of that. For the assessment, we have homework quizzes that will contribute. You will find exactly on Brightspace the description how your grade will be built up from homework quizzes, from the design of the active antenna, and from the final exam quiz. So the details for this are completely on Brightspace. So this is about the introduction to this course. Here you find also on Brightspace, this is the same as in Brightspace, you find this prerequisite knowledge, and you find the link to the homologation program, which is here. It is just this whole homologation program with all the topics, and the topics, just everything has the same layout as what I'm doing now. And for example, if you go to a topic, then probably there will be like a video. You see, here's a video, you can look at the video. So if you're missing a topic, you can find it in this way. Then I would like to introduce you the complete program for this course, that you can judge yourself if you are now in the right classroom, because if not, then, well, it's time to leave, I would say. But I hope this is what you are looking for. So we have 17 lectures, and I will go through all the lectures. It's a plan that we do. Maybe we will, if there will be problems, we go too fast or too slow, we can adjust it a little bit. But basically, this is the idea about the program that we have. Today, we will talk about the principle of amplification and biasing. Basically, in the bachelor course, we used operational amplifiers as controllers in feedback systems. So there wasn't much in designing on transistor level. Basically, there was nothing at all. And we had already a device that, together with a power supply, was capable of providing an available power gain larger than unity. So it was it could be applied as an amplifier. But now we are going to use in CMOS technology. And we want to start really at the beginning. So how does this principle of amplification works, and what is the principle of biasing? Because we have seen that many students or participants are struggling with this in a later phase of the course. So we better pay some attention at the beginning of the course to this. So today we will do this. And there will be a poll, and there will be a homework quiz with a few questions, not too much, because we know that Thursday is already in the next lecture. So we don't want to create a lot of stress. So this today is the principle of amplification. So we are not really focusing on the MOS characteristics. We assume that everyone knows about the behavior of MOS transistors. But in the lecture next, then we will dive a little bit more into amplifying devices. And if you look on this page, you see some model parameter. It's not, it's just, you know, a page to look at and not really to discuss all the details. But if you look to modern simulators, there is really a lot of parameters necessary to understand or to model the behavior of the MOS transistor. And this is too much to deal with during this design. So what we want to teach you here is how can we use the graphs and how can we use simplified models to help us to take important design decisions for noise, for bandwidth, for current and voltage drive capabilities. And a very convenient model that can help us also is the EKV model. And it is not in the bachelor program of the University of Delft. So we'll pay a little bit extra attention to that because there's a very important parameter like the inversion coefficient that can be used for designing amplifier stages. So that is done in, or actually we will do that on next Thursday already. So, and then we know about, let's say, how we model this device. We know that we can use a MOS transistor as an amplifying device together with bias sources. And then it is time to study more in detail the behavior of this basic amplifier stage. So we are going to look at its drive capabilities, its nonlinearity, its dynamic drive capabilities, its small signal behavior, its noise behavior. How does it behave if we place it between a source and a load? What will be then the transfer? All kinds of aspects we will dive into detail. Well, here in this lecture, we will only do it for the static and dynamic behavior. And the next lecture, we will dive into the noise behavior. So we will study the noise behavior of a single MOS transistor and, for example, study can, for example, a certain noise performance can it be achieved with such a transistor? Maybe the process isn't good enough. Maybe we have a showstopper. And well, it is useless to go on with your design if one of the essential things cannot be realized. So how can we find the very early stage of the design parameters that tell us is the noise achievable, the noise performance, and what shall we do about it? How do we have to design it? So that is basically what we are studying then in this lecture. And of course, as I told you, we want to do this all we want to illustrate the application of this knowledge all in the active antenna. So now, if we know the behavior of such a CS stage, then we can say, okay, let's design a CS stage that can drive the load for the active antenna that has a good noise performance and see what kind of device, what kind of width and length and voltage and operating current we need to get this behavior. And maybe in these requirements for these parameters like WL, etc., is an overlap for the static behavior and for the noise performance. And if so, then maybe we can make it with a single stage. That would be nice. So then the work that you will do in groups or individual is design an amplifier stage and evaluate the performance of a single stage biased CS stage and see if we can use it for the antenna amplifier. So is the gain accurate enough? Is the noise okay? Can it drive the load for the antenna? And is the nonlinearity okay? And if it is all okay, then we have our amplifier. But okay, as you see, we are only in lecture 5 and we have 17 lectures. Probably it will not be okay. We need to do some extra. So that's why I have this crying puppet here to tell you that we need to go on and see if we can improve this stage. And in structured electronic design, we have techniques for improvement. And that's a limited number of techniques. And we call them error reduction techniques. And one technique is compensation. If you have an error, maybe we can compensate for the error. So, and what kind of compensation techniques do we have? An important compensation technique that we have is balancing technique. So we will introduce you the principle of balancing, because this is your concept. You have some effects, you don't want it, you add the opposite and then it's gone. That is additive compensation, basically. And then we are going to apply this and use network theory to apply this to the single CS stage that we have studied thoroughly. And then we find two very interesting structures, and one is called the differential pair. You know it as a differential pair, but our road to this differential pair is completely different. It is a road from the common source stage to the application of a balancing technique that will give us the differential pair. And if we now know in which way balancing affects the behavior of a stage, then we don't have to calculate everything again. We have already calculated everything, its performance for the CS stage. And if we know the behavioral modifications due to balancing, we can predict how a differential pair will behave, what the noise behavior will be, how the poles and zeros will be, and of course also what is the change in the nonlinear behavior. And the same we can do for another balanced structure, which is then the complementary parallel or the push-pull stage. So we do it in a similar way. We find another stage, a push-pull stage. We study its biasing and we find the characteristics. Not by thorough analysis of this stage, again, like we did for the CS stage. No, simply by studying the behavioral modifications as a result of the application of balancing. And this we can also do for another error reduction technique, another error reduction technique that we have already studied in the bachelor phase, which is negative feedback. If we know in which way a stage behavior changes or an amplifier behavior changes if we apply negative feedback, then we can predict the changes if we go from a CS stage to a CS stage with feedback. So that is basically what we will do. We have introduced a nuller as an ideal controller in a negative feedback system. And we will say, okay, it's not perfect, but let's now identify the CS stage, the biased CS stage as a nuller. Let's say this is our most simple nuller amplification. And maybe a balanced stage, because we also know now about the balanced stage. So if we put this one or this one in our feedback structure, we get this for the voltage follower. We can say, okay, here's a nuller structure. Here we put a MOSFET in it. And now you recognize the common drain stage. But we don't have to calculate the common drain stage, everything again. No, we know what kind of feedback technique we applied and can predict in which way this common drain stage, the performance will deviate, will be changed by the application of negative feedback. And we can do this for a lot of stages. Here below, you see a lot of feedback stages, and we don't have to go in detail for all these stages. No, we can simply predict their behavior from the application of negative feedback. And now we have a really interesting palette of stages. We have all kinds of stages that we can combine somehow together to create our antenna amplifier. And this will be one, let's say, one of the bigger assignments for you to say, okay, you will find out that the single stage solution is not good enough. Well, maybe we can use two stages and we can combine a feedback stage with a CS stage or a balance stage or whatever. So you can combine stages and see if combined with cascaded stages, so one stage connected to the output of the other one, if you can then make an amplifier that would be good enough. But of course, you know from the previous course, and most people know from their bachelor, that negative feedback with only one controller and one controller, maybe with multiple stages, is a much better option. And that's our next step of investigation. But then we have questions like, how many stages do we need? So if I make a controller with multiple stages and one feedback loop around it, how many stages should be in it? And if the answer can be calculated up front before we do it, before we put anything in LT-SPICE or whatever, that would help a lot. Because if the answer is like 5 stages, then I wouldn't start, because probably you will end up with so many poles that it will be difficult to keep the whole thing stable. So it would be nice to have a number and telling, let's say, okay, it's not that high, it's low, so we can make we can do the design. And if it must be high, then maybe we need 2 amplifiers, 2 feedback amplifiers. But if we connect stages in this controller, how do we interconnect them? What is the rule for interconnecting them? Because this is done always intuitively by designers, but there are many ways of connecting stages together, and sometimes you can get interesting solutions for that. And what type of stages should we then use? What type of stage should we use at the input or at the output or for intermediate stages? And if we put those stages together, can we then still um, predict the behavior? Because then the small signal model will be so complex that it will be difficult to predict the poles and the zeros and the stability of the amplifier. So how can we make it predictable? How can we reduce the interaction between stages in such a way that we're also sure that we need a minimum number of stages for the maximum performance? So that's what we are going to do in this lecture about designing multiple stage controllers. And then we are going to put it all together in the antenna amplifier. We have an overall feedback antenna amplifier. We are going to design step by step, the drive capability, the noise performance, and the bandwidth, and see how many stages we need. And then you see the thing is we have enough stages, we have enough bandwidth, but we didn't talk yet about stability. That's another thing. That's the filter response. That's the dynamic response of the amplifier. So maybe we have enough bandwidth, but maybe the thing is unstable. So we have to do something about it. And that's when frequency compensation comes in. Now, in the uh, bachelor course, we talked about phantom zero compensation, and phantom zero compensation is probably not known to all students coming from abroad. Maybe they didn't do this. And since it's a very important topic, this will be a topic that we give a short recap during this course so that everyone knows, okay, this is intended. And we also give a demonstration with a single bipolar transistor, because the thing has a higher gain than the MOS transistor, and we can easily make it unstable, just have a single stage, and then illustrate phantom zero compensation. But in this course, we will also introduce other compensation techniques, pole splitting, pole zero canceling, resistive broadbanding, and we will also see what happens if you only focus on phase margin, which is common practice. So that is important because maybe the common practice is not always the good practice. And then, of course, the next step is to apply this in the antenna amplifier. So we are going to compensate the antenna amplifier. And now, if we have a small signal model of the amplifier that turns out to be stable under all conditions, then we are going to start with the biasing, because earlier is no use. It makes no sense, because if we are going to bias something and study something in LT spice which is unstable, then probably you have convergence problems. It doesn't work at all, and you are only struggling with your simulator. So first, we will make the whole thing in a small signal model stable, and then we go to LT spice to finish the thing in the biasing. So we must talk about how to bias all kinds of stages. And the concept, so making all these sources in inconvenient places, and then about the implementation of the sources. And if we did that, then we'll complete the design of our antenna amplifier and do the final verification of the behavior in LT spice. And well, this is the one we did last year, but this year it will probably be different because we changed the specs a little bit. So, but this gives you some idea about the complexity at the end of the course that you can completely manage, because the idea is that you understand everything here in the circuit. There are no questions at all. You know exactly what all the components are doing and why they have the value that they have. That's the intention of this course. And then we are going to do the recap, putting everything together, do the mini masterclass, and maybe we can even set up a design sequence, a flow chart for amplifier design. That would be nice, because then maybe we have some people who want to program it, and then you have your program for amplifier design. That's at the end, of course, what we want.